Hello everyone. So, welcome to a lecture series on essential mathematics for machine learning. So, this is our first lecture on basic concepts of calculus. So, let us start what the essential part of calculus which is used in machine learning. So, the term machine learning basically refers to learning from empirical data which could be in the form of images, observations, patterns or records. Machine learning aims at performing well on the training data and also at ensuring a good performance on future unseen data. So, this is the main purpose of any machine learning, that whatever training data we are having, we train that accordingly and we try to predict the future. We develop an algorithm to try to predict the future. Okay. Machine learning deals with minimizing a cost function, also called as objective function, which is a scalar function of several variables that typically measures how accurately our model fits the data we have. So, that is the main important theme of optimization here. Calculus and optimization play an important role in understanding the algorithms of machine learning. So, let us first start with calculus, that what are the various components of calculus which we are having and which are essential in machine learning. So, the first is, before going to the various other aspects of calculus, let us first understand functions of n variables. So, what do you mean by function of n variables? Let us suppose as a subset of Rn. So, what do you mean by Rn? So, let us see Rn is what you mean by Rn. Rn is basically, if you take Rn is basically a set of n tuples x1, x2 up to xn such that xi belongs to R for all I. So, this is basically Rn. If you take R2, suppose if you take R2, what is R2? R2 is basically all xy such that x and y belongs to R. That means two dimensional geometry, if we speak in geometry point of view. So, R2 is nothing but a 2 dimensional geometry, R3 is basically 3 dimensional geometry. So, Rn is basically n dimensional space, which is x1, x2 up to xn such that all xi belongs to R. So, if we take a S, a subset of Rn, and we define a function f from S to R, okay, in this way, suppose w equal to f of x1, x2 up to xn, then this function is called function of several variables or function of n variables. So, here this xi, here this x1, x2 up to xn are called independent variables and w is called dependent variable. Okay. So, we have already seen a function of single variable. In the same way, we are trying to extend the function of single variable to function to n variables. Okay. Now, how we can define domain and range of function of n variables? So, again consider a function f from Rn to R, which is defined as z is equal to f of x1, x2 up to xn. Now, domain of the function is defined as the set of all the points x1, x2 up to xn in Rn for which this function f is defined. So, that is called domain of f, and the range of f is simply the set of all images of the point x1, x2 up to xn of the domain set denoted by R of f, range of f. So, let us discuss what do you mean by domain or range of a function by giving some examples. Say we take a function f from R2 to R, and the function f is defined like this: f of xy suppose is equal to x square plus y square. A simple example, suppose function is, so here we are having two input variables. So, this function is a function of two unknowns and the image is giving this f maps this to R, which is x square plus y square. So, what will be the domain of this function? See, that domain of this function, domain of f will be nothing but entire R2, because it is always defined for every x and y. If we talk about range of f, so range of f are all those see you are having this R2 and here it is R. Okay. We are what xy we will choose here, so that f is defined, that is called domain of f, and through this map, this f suppose map to this set. So, this set is basically range of f. So, here what will be the range? See this value x square plus y square can never be negative. X square plus y square for every x and y in R is always greater than or equal to 0. It may be 0 when x and y both are 0. So, we can say that range of this function f will be from 0 to infinity. Okay. It can never be negative. So, the range, the domain of this function is entire R2 and the range of this function is from close interval 0 to open interval infinity. So, in a similar way, suppose take another example, let f is from R2 to R and say f is defined by this, f is defined as under root of say y minus x square. Okay. So, again for this f there are two input variables x and y and it maps those 2 points in this way by the mapping under root y minus x square. So, what will be the domain of f? Domain of f is all those points where this f is defined, and this f is defined whenever y minus x square is greater than or equal to 0. Otherwise, this f is not defined in real lines. So, we can say that domain of this f will be all x y such that y minus x square is greater than or equal to 0. So, the collection of all those x y where y is bigger than or equal to x square will constitute the domain of this function f. Now, if we talk about range of this function f, so range of this function f will be, now whatever x y you choose here, this will map x y to in this way, and under root can never be negative. Okay. So, this may be 0 when x and y both are 0, or y equal to x square, if y equal to x square it will be 0. So, we can say that range of this function will be again for this example 0 to infinity, close interval 0 up to infinity. So, in this way we can define domain and range of several variable functions. Okay. Now, come to partial derivatives. How can we define partial derivatives? So, here is an example, here consider a function of n variables which is given by z equal to f x1 x2 up to xn, and then the partial derivative of f with respect to xi is defined like this. So, let us understand what you mean by this. See, we all know what is function of single variable if function is f is from R to R. If f is from R to R, we all know that we define dy by dx, which is nothing but limit h tending to 0 f of x plus h minus f x upon h. So, this is provided this limit exists. So, this is called derivative of the function f with respect to x. In this way we defined f dash x at x. Okay. If we define dy by dx at x equal to a, then at x equal to a in the same way we can define like this, limit h tending to 0 f of a plus h minus f a upon h. Now, let us come to function of two variables. Say w is equal to f of x1 x2, okay, where f is from R2 to R, a two variable function. Now, here you are having two independent variables x1 and x2, and w is a dependent variable. So, here we have a concept of partial derivatives. So, if we define del f upon del x1 So, del f1 del x1 is nothing but limit h tending to 0, it is f of x1 plus h keeping x2 fixed minus f of x1 x2 upon h. If we are dealing with partial derivative of f respect to x1, then this h will be only with x1 and the other part will be x1 x2. Similarly, if we define del f upon del x2, then it may be defined as limit k tending to 0 f of x1 x2 plus k minus f of x1 x2 upon k. Okay. So, in this way we can define first order partial derivatives. So, these are called basically first order partial derivatives, first order partial derivatives. With respect to x1 and x2, provided these limit exist. Okay. In the same way, if the higher order derivatives, suppose f x1 x1, if we have a function w of two variables x1 and x2, where f is a function from R2 to R, then the higher order derivative, second order derivative may be defined as del of del x1 of f x1, which is nothing but second order derivative of f respect to x1. If we want to define del x2 x2, that means second order derivative of f respect to x2. If we want to define del x1 x2, so this means f of x1 with respect to x2, and that means del by del x2 of f x1, and that simply means second derivative of f respect to x2 x1. And similarly, other higher order derivatives, partial derivatives can be defined. So, let us understand this by a simple example, simple illustrations. So, let f is function from say R2 to R, okay, and let f of x y is given as, let us suppose it is given by x 4 minus x square y square plus y raised to power 4, and we have to find f x, f y, suppose f x x, f y y, f x y at minus 1 comma 1. Suppose this we want to find out. So, how we can find? This is very easy problem. So, let us discuss. So, f is what? F is x raised to power 4 minus x square y square plus y raised to power 4. So, f x is what? The first order partial derivative of f respect to x. So, if you want to differentiate partially f with respect to x, that means we have to treat x as a variable and all other variables as constant. So, that means it is 4 x cube plus 2, it is minus, sorry, minus will come here because it is negative. So, this is negative of 2 x y square. So, f x at minus 1 comma 1 will be, you substitute x as minus 1 and y as 1. So, this will be minus 4, this will be minus plus 2. So, the value is minus 2. Okay. Now, if you want to compute f y, it is what? Del f upon del y, which is, now if you want to partially differentiate f with respect to y, so you will take y as a variable and all other variables as constant. So, you take this will be 0, now this will be derivative of y square with respect to y will be 2 y. So, that is minus 2 x square y plus 4 y cube, and f y at minus 1 comma 1 will be nothing but, it will be, we have to put x equal to minus 1 and y as 1. So, it is minus 2 and it is again plus 4. So, it is 2. Now, suppose you want to compute f x x. So, what will be f x x? It will be second derivative of f respect to x. So, it is nothing but del by del x of f x. f(x) we have already computed. So, again differentiate partially with respect to x. So, that means 12x square minus 2y square. Now, put x equal to minus 1, y is equal to 1. So, the value of f(x)(x) at minus 1 1 will be equal to 10. Okay. Now, suppose you want to compute f(y)(y) now. F we have already computed. So, what is f(y)(y)? It will be del square f upon del y square, which is del by del y of f(y). So, f(y) we have already computed. So, f(y) is basically minus 2 x square y plus 4 y cube. So, that will be del by del y of minus 2 x square y plus 4 y cube. So, this will be equal to minus 2 x square plus 12 y square. Now, at minus 1 comma 1, it will be minus 2 plus 12, which is again 10. Okay. Now, the last is f(x)(y). f(x)(y) means del square f upon del y del x. That means del by del y of f(x). So, this is del by del y of. Now, what is f(x)? f(x) is 4y cube minus 2xy square. So, it is 4y cube minus 2xy square. So, it is it is 4x cube. It is 4x cube minus 2xy square. So, this is 12. So, this is 0 minus it is 4xy, and the value of this at minus 1 comma 1 will be nothing but 4. So, in this way, by the simple mathematical calculations, we can compute the first order partial derivatives, second order partial derivatives, or higher order partial derivatives. Okay. Now, why we are studying this? So, because these concepts are important in machine learning. Whenever you develop an algorithm, okay. So, in developing those algorithms, you need the knowledge of basic calculus. So, gradient concept is very important in machine learning. And what do you mean by gradient? How we define gradient? Gradient is basically of a function f from Rn to R, which is a seven-variable function, is denoted by del of f, and is given as by this vector, that is del f upon del x1, del f upon del x2 of this. So, let us understand what you mean by this. So, here you are having a function f from Rn to R. Okay. Function is of n variable. N variable are the input variables, and function maps to R. Now, del of f is nothing but is a vector of this type, del f upon del x1. First we differentiate this with respect to x1, then this with respect to x2, and so on with respect to xn, and we take it as a column vector. Okay. And suppose you are having a function, say f of from R to R3 to R, and it is defined like this. Suppose f x y z is defined like this. Suppose it is x cube minus 3xy square plus x square y plus y cube, suppose plus z y. So, suppose this function you are having, and you want to compute gradient of f. You want to compute gradient of f. Gradient of f is to compute at say minus 1 0 1. So, you want to compute gradient of this f at a point say minus 1 0 1. So, how we can proceed? So, simply we have to find out the first order partial derivatives of f with respect to x, y and z, and we will compute these first order partial derivatives at this point, that will give gradient of f at this point. So, let us complete this problem. So, what will be f x? F x is 3x square minus 3y square plus 2xy. Okay. So, f x at minus 1 0 1 will be. So, if you take f x as minus 1 0 1, so this will be, this is 3 this is 0, this is 0. So, it will be 3 only. Now, you compute f y, f y will be what? F y will be minus 6 x y, okay, plus x square plus 3 y square, and f y at this point minus 1 0 1 will be. So, y is 0, only x is here. So, it will be 1, yeah, okay. So, it will be plus z also, and z is 1. So, it is 1 plus 1, that is 2, okay. And f z will be what? F z will be only y. So, f z at minus 1 0 1 will be this will be 0. So, now what will be gradient of f? So, gradient of f at this point minus 1 0 1 will be this vector, this 3 2 0, this transpose. So, this will be the gradient of f. So, in this way we can find out gradient of f, but this small term gradient of f plays an important role in various aspects. So, let us understand this one by one. Now first come to directional derivative, then we will see more geometrical interpretations of gradient of f. So, what do you mean by directional derivative of f? So, let us discuss that again. So, the thing is directional derivative. See, if we take a function of two variables x and y, so we normally compute del f upon del x or we compute del f upon del y. So, what is del f upon del x means? Del f upon del x geometrically means that rate of change of f along x axis. Okay, you are having x axis and y axis. So, what is the rate of change of f along this axis? That will be computed by del f upon del x. If you are interested to find out what is the rate of change of f along y axis, so that can be computed by del f upon del y, that is the rate of change of f along y axis. We normally deals only two directions, either x axis or y axis. But if we ask that what will be the rate of change of f along any direction u, so how can we compute the rate of change of f along any direction u? So, that comes from directional derivatives. So, how it comes from directional derivative, let us see. So, the rate of change of f along any direction, this is a parameter s, along any direction u at a point p naught is given by, suppose p naught is this point, suppose p naught is x naught y naught. Here I am taking a function of two variables. In the same way I can extend the concept to function of n variables also. Okay. So, if I am taking a fixed point p naught as x naught y naught and u is a direction, u is given as u1 I cap plus u2 j cap, where u is a unit vector, that means mod of u is 1. Okay. So, the rate of change of f along u at a point p naught is mathematically defined as limit h tending to 0 or limit s tending to 0, sorry, limit s tending to 0 f of x naught plus s u1 y naught plus s u2 minus f of x naught y naught upon s. So, mathematically it can be defined like this. So, provided this limit exists, provided the limit exists. So, this is y naught. So, this is the definition of finding directional derivative of f along any direction u at a point p naught. See, if you take considering x axis, so that means in the x axis u will be what? I cap only. Okay. The I cap means u1 is 1 and u2 is 0. So, if you put u1 equal to 1 and u2 equal to 0 here, so this definition is nothing but del f upon del x. And if you are taking u along y axis, So, in y axis u is nothing but j cap. So, if it is j cap, that means u 1 is 0 and u 2 is 1. So, if u 1 is 0 and u 2 is 1, you substitute here. So, that is nothing but del f upon del y. So, in that sense we can say that this definition generalizes the definition of del f upon del x and del f upon del y also. So, the first way of finding a directional derivative along u in the at a point p naught is this limit definition. Now, if the function is if the first order partial derivative function exists at a point p naught, then this definition can be further extended. So, how we can extend this? Let us see. So, you are having a fixed point x naught y naught, which I am calling as p. This is a direction u, which is given by u 1 I cap plus u 2 j cap. It is a unit vector, mod of u is 1, I am assuming, along u, which is a unit vector. Suppose now x and y are any point on this vector in this direction, x y is any point. Okay. So, how can you find the equation of this line in the direction u? So, the equation of line can be found by x minus x naught upon u 1 is equal to y minus y naught upon u 2, because x minus x naught and y minus y naught are drs of this vector and u 1 u 2 are also drs direction ratios of this vector and both are parallel. So, the ratios will be same. So, suppose it is equal to s. So, what this implies? It implies x is equal to x naught plus s u 1 and y will be equal to y naught plus s u 2. Okay. Now, you want to compute directional derivative of f at p naught in the direction u. So, that will be equal to. Now, this f you want to differentiate f with respect to s. So, this f is a function of x and y, and where x and y are the functions of s. So, here this function is function of only one variable because see this is see this x naught is fixed, u 1 is fixed, direction is fixed. So, this x is a function of only one parameter s. So, instead of partial derivative here will be a total derivative, okay, plus del f upon del y into del y, again it is dy, because again it will be a single variable function. So, this will be nothing but dy upon ds. Okay. Now, what is del f upon del x? You leave it as it is. Now, this at a point p naught, of course, and this at a point p naught. Okay. So, this is del f upon del x at p naught, and what is dx upon ds from this equation is u 1 plus del f upon del y at p naught, and what is del y upon del s from here is u 2. So, this is nothing but del f upon del x at p naught I cap plus del y upon del f upon del y p naught at this j cap dot with u 1 I cap plus u 2 j cap. It is nothing but the dot product of these two vectors, and what it is? It is nothing but gradient of f at p naught, and what is this? This is nothing but u vector. So, this is u vector. So, we can say that if first order partial derivative of function exists, then the directional derivative of f at a point p naught in the direction u is nothing but the dot product of gradient of f at that point with the unit vector along that direction, the direction in which we want to find the directional derivative of f. Okay. Now, let us try to understand the geometrical interpretation of this. See, we have seen that the directional derivative of f at p naught in the direction u is nothing but a dot product of gradient of f at p naught with u vector, where u is nothing but again it is u 1 I cap plus u 2 j cap, which is a unit vector, mod of u is 1. Now, a dot b is what? A dot b is mod of a mod of b into cosine of angle between them. So, this is nothing but mod of this vector, mod of u and cosine of angle between them. This theta is the angle between gradient of f at p naught and vector u. Now, mod of u is 1 from here. So, this is nothing but del of f at p naught into cosine of angle between them. Okay. Now, if you want to see that which is the direction of f where the rate of change of f increases most rapidly or decreases most rapidly. So, that can be seen from this expression. How? See, this expression will maximum when? This expression will maximum if cos theta, this is a fixed quantity, at p naught it is a fixed quantity, it will not change, but this will change, the theta will change. So, in which direction, because we do not know which u is, we want to know that which u, which is the direction u at which the rate of change of f increases most rapidly. So, that in order to find that direction, this cos theta must be maximum. So, del df upon ds at p naught in the direction u is maximum if cos theta is maximum, and cos theta maximum means 1, because cos theta lies between -1 to +1, the maximum value of cos theta is 1. If cos theta is 1, this means theta equal to 0. Theta 0 means what? Theta 0 means the direction of u is same as the direction of gradient of f of p naught. So, that means du is parallel to direction of f at p naught. That means the rate at which the f increases most rapidly is along the direction of gradient of f. So, if we compute gradient of f, it gives what? It gives the rate at which the rate of change of function increases most rapidly, and we sometimes call this steepest direction. Okay. So, similarly, if you want to see df upon ds at p naught in the direction u is minimum, when it is minimum? It is minimum if cos theta is -1, that means theta equal to pi. So, this pi means the direction of u is nothing but is negative of gradient of f at that point. So, if direction of u is see gradient, if it is opposite to a direction of gradient, that means that is a direction where it decreases most rapidly, it is a descent direction. This is a ascent direction, it increases most rapidly, and this is a descent direction where it decreases most rapidly. So, if a function is given to us, maybe of 2 variable or 3 variable function, and a point is given to you, and if you want to find out the direction where it increases most rapidly or decreases most rapidly, that will be simply given by gradient of f at that point or negative of gradient of f at that point. So, let us discuss it by another example. Suppose you are having this function, say you are having this function f x square y plus y square x plus z square x, x square z, suppose x square z and z square x. Suppose p naught is, you can take any point, say p naught is 1 0 1. Now, the question is, for this function, which is this function is again, this function is from R3 to R, of course, there are 3 input variables x, y and z. So, this function is from R3 to R. Okay. Now, if we want to find out the rate at the direction where the rate of f increases most rapidly, so that will be gradient of f at that point at p naught. So, what is gradient of f? It is del f upon del x, del f upon del y, del f upon del z, because there are 3 variables here at p naught. So, this will be further equal to What is del f upon del x? It is 2 x y plus z square. Del f upon del y is x square plus 2 x 2 y z. Del f upon del z is y square plus 2 z x at a point 1 0 1. So, this is nothing but x is 1, y is 0. So, it is 0. So, this is 1, x is 1, y is 0, z is 1, this is 1, so this is 2. So, this transpose. So, this is this direction is the direction where f increases most rapidly. So, this direction is basically if you see this direction, this is I cap plus j cap plus 2 k cap upon under root of 1 plus 1 plus 4, that is I cap plus j cap plus 2 k cap upon under root 6. So, this is a direction where f increases most rapidly. If somebody asks you that how we can find out a direction where f decreases most rapidly, so that is nothing but negative of this, negative of gradient. So, the direction where f decreases most rapidly is simply negative of gradient of f at p naught, which is equals to minus I cap minus j cap minus 2 k cap upon under root 6. So, in this way we can find out the rate of change of f along any direction, and okay. So, this is direction derivative. So, here I have defined for 2 variables and then for n variables the rate of change of f. So, this I have already explained you that gradient of f at x points in the direction of steepest ascent of x, where it increases most rapidly, that is steepest ascent, and where decreases most rapidly, that is called steepest descent, and that is nothing but negative of gradient of f. Okay. So, thank you very much for hearing me. Thank you.